Force on a current-carrying conductor in a magnetic field, the motor effect. In this module, you'll learn about the force on a current-carrying conductor in a magnetic field, which is called the motor effect. Place a current-carrying wire in a magnetic field. What do you observe? You'll observe that the wire experiences a force. This is called the motor effect. Want to observe the motor effect? Well, hang a wire swing between the poles of a C-shaped or horseshoe magnet as shown here. When you close the circuit, you'll observe that the wire is thrown outward. From this, you can deduce that a wire carrying a current experiences a force when placed in a magnetic field. You will now investigate this force on a current-carrying conductor in a magnetic field in an experiment. You'll require a stiff wire, a strong permanent magnet, a 9-volt dry cell, a switch, and insulated copper wires. Here's the procedure. Bend the stiff wire ABCD into the shape of a swing, as shown here, and then connect it to the copper wires, dry cell, and switch to form a circuit. Now place the south of the magnet over part of the wire BC. Switch on the current and observe the direction in which the wire swings. Next, reverse the direction of the current by switching the polarity of the dry cell. Now invert the magnet so that the pole above the wire swing is now the north pole. Now again switch on the current and observe the direction in which the wire swings. What do you observe? First, with the current flowing in the direction ABCD, the wire swings outwards from the magnet. Second, if the current is reversed, the wire swings in the opposite direction, that is inwards. And third, if the magnetic field is reversed, the wire swings outwards again. In the experiment, you'll observe that the swing moves outwards when current flows through the wire B. You can thus conclude that a force acts on the current-carrying wire when it is placed in a magnetic field. This force acts perpendicular to both the direction of the current and the direction of the magnetic field. You'll notice that the direction of the force is reversed when you reverse the direction of either the current or the magnetic field. How will you deduce the direction of the current-carrying wire when it is placed in a magnetic field? Well, by applying Fleming's left-hand rule. Point the thumb, forefinger, and second finger at right angles to one another as shown here. Now point the forefinger in the direction of the magnetic field from north to south direction, and the second finger in the direction of the current. The thumb gives the direction of the motion of wire, that is, direction of the force. But why does a current-carrying conductor experience a force when placed in a magnetic field? To answer this, you must examine the combined magnetic fields due to the current in a wire and a magnet. These two figures show the magnetic field due to the current flowing through a wire and the magnetic field due to the magnets, respectively. And this figure shows the superimposed field patterns of the magnet and current-carrying conductor. And the last figure shows the combined magnetic field when the wire is placed between the magnetic poles. From the last figure, you can see that there is a stronger field on one side of the wire at A. This is because all the magnetic field lines are acting in the same direction. At B, the magnetic field lines of the current oppose those of the magnet, making the combined field weaker. A force then acts on the wire from the stronger field to the weaker field. Bet you enjoyed learning. In this module, you learned the following. A current-carrying conductor in a magnetic field experiences a force which is called the motor effect. The force experienced by a current-carrying conductor acts perpendicular to both the direction of the current and the direction of the magnetic field. Also, the direction of the force is reversed when the direction of either the current or the magnetic field is reversed.